Right, so back here, yesterday we did this first Kirchhoff table. I'll help you guys out with the rest of these here. So number 2, I think, is probably the toughest one, right? Toughest one, right? Right, so you guys got some paper out, right? Because we're gonna draw some equivalent circuits, which is gonna help us solve this table, right? So again, I have a bunch of different versions. My numbers are probably different than yours, right? Most of these Kirchhoff tables, they came out with whole numbers, right? There's a couple of exceptions. There might be like 1.5 watts or something somewhere, right? But most of these are whole numbers, right? Right, and I gave you each individual resistor. So on number 2, there's 5 resistors, and I gave you the voltage supplied by the battery, right? You guys remember battery supply some amount of voltage, like this is a 9-volt battery, AA is like 1.5 volts, right? My paper here has a 24-volt battery, and yours is whatever's printed on your paper. Okay? So can we figure out what's the equivalent resistance for the whole circuit? Is the first thing we're gonna figure out. Then we're gonna say what's the voltage drop across each individual resistor, right? What's the current flowing through each part of the circuit, and finally, what's the power in watts at each point. Very good. Right. So, you guys got the paper out? That'd be good. I'm gonna take this little circuit and blow it up bigger on this paper. Okay. Yeah. So here's my voltage source on the left. Right. The 2 parallel lines, one longer than the other. Here's a battery. Positive terminal, negative terminal. Okay, I've got 24 volts. 24 volts. Right. Then I've got this resistor E, which on my paper is 3 ohms. So I'll do 3 ohms right there. Right. I got this resistor D up here, which on my paper says 2 ohms. I got resistor C down here, which says 1 ohm on my paper. And then B and A, which are 6 and 6 ohms. All right, there you go. So that's just the circuit as it was given. Okay. Oh, first thing I need to figure out is what is the total equivalent resistance? Right? Like this 24-volt battery feels like it's pushing against effectively 1 cumulative resistance. What is that resistance? And there was a process that we walked through a few times yesterday, so maybe this is a good warm up today too. Right? And the process goes like this. Because remember, you're going to find your voltage source, which is on the left side of the circuit here. Okay? Fly over to the complete opposite side of the circuit. Okay? And then start making equivalent resistances and work your way back towards the voltage source. So we did a few of those yesterday. So you want here. So I'm looking at these 2 in parallel. This is resistors A and B. Oh, I was going to ask you guys series or parallel, but you guys would have said parallel, right? Because whatever current happens to make it to that part of the circuit, it's going to hit this junction. It's going to split and be pushed through both of these A and B simultaneously. Yeah, that's parallel. Okay. So it has 2 parallel resistors. What's the equivalent resistance of those? Can I simply add them, or do I have to treat it like 2 guys painting a fence? How many guys say like 2 guys painting a fence? That'd be that, right? Okay. Ooh, speaking of that analogy, if it was 6 hours to paint a fence and 6 hours to paint a fence, 2-man team, how long would it take them? Probably like 3 hours. I bet this is going to be collectively like a single 3 ohm resistor, right? Or you could just do product over sum, right? So I'll say resistance equivalent is, so product over sum, number of ohms, got 36 on 12. Yeah, that's definitely 3 ohms, right? So now I can redraw my circuit. I'm going to do this a few times, by the way. So ready for that. Redraw my circuit. Okay, so I still got my voltage source, right? I still got this resistor E, haven't touched. So I got this guy, haven't touched those, right? But these 2 guys collectively, it's as if it's a single resistor that's now only this many ohms. Should have solved. Okay. You guys good? Okay. Actually, that middle equivalent step, this is going to be important later. So in your notes, since you guys are drawing these in your notes, right? Definitely hold on to this one because it's going to help us out in a few minutes. Okay. But I'm going to keep going. Okay. So again, I'm working back towards my voltage source. Oh, now I ran into these. Now, guys, these 3 resistors are all in what with each other? Series or parallel? How many guys say series? Who says series? Yeah. So they're all on the same street. So one of the analogies I was using for current yesterday was traffic flow, right? So if there's like a like a line of cars. All cars have to go through these 2 stoplights and then these 3 stoplights and then this stoplight. Right? They're all on the same street. Right? They can't like split and go different. Right? So, can I just very simply add these 3 together? Right? So 2 ohms, 3 ohms, 1 ohm. That's 2, 3, 4, 5, 6. That's 6 ohms. So the equivalent resistance for that branch, that entire branch, is like 6 ohms. Right? Just add them together. Right? That okay so far? Right? Right, so now I can go to the next step. I'm going to redraw my circuit again. So picking up from that point. Right, got my voltage here, so many volts. I got this resistor, right? And then these 3 collectively, it's as if there's just a single resistor that's this many ohms right there. Okay, you guys good so far? You guys keeping up with your own paper too? Right. So then working back towards the voltage source, now I run into the final resistor. Now these resistors are in what? Series or parallel with each other? Who says series? Who says parallel? Yeah, parallel. Right? You know that because whatever current's making its way around is going to hit this junction and split. Right? So the traffic analogy is if you're driving around town, okay, so you leave this parking garage, which is the battery, right? You're driving around, right? You hit this junction and you say, I could turn to the right and go down these 3 stoplights, or I could go to the left and hit 6 stoplights. You guys think that most of the traffic is going to go along 3 stoplights? I'm just thinking ahead to current later. Let's go, right? Okay. So most of the traffic is probably going to go that way, but some of the traffic is, well, okay, now it's getting kind of jammed down that road. So a little bit of the traffic's going. Right? But anyway, that's for current for later. But for now, I just need to figure out what's the equivalent resistance, and I can do product over sum because they're in parallel. So the total equivalent resistance for the entire circuit is, say, 3 times 6 over 3 plus 6. Number of ohms. That's 18 on 9. It's like 2 ohms, right? In fact, I think that makes sense too from the painting a fence analogy, right? If it was 3 hours to paint a fence for this guy, 6 hours to paint a fence for this guy, 2-man team, yeah, they knock out the job in 2 hours. Yeah, that makes sense too, right? Again, like all this electricity circuit stuff does have applications of like people working in teams, traffic flow around a town, water flowing around a pipe system, right? You can take all these concepts and it has all these cross applications, right? So my final equivalent circuit is very simply going to be my 24-volt battery, which I was given, and all these 5 resistors are collectively acting as though there's a single 2 ohm resistor, right? That's the final equivalent circuit. Right? You guys get that? Right. And that is the first number I can write on this table. I can say, what's the equivalent resistance for the entire circuit? 2 ohms. 2 ohms. Right? Right. Right. Do you guys get a equivalent resistance for your circuit also? While you guys are maybe finishing that up and checking your work, it's probably a whole number. It should be a whole number, I think. I'm going to draw the waterfall model for this too, because that helps visualize this. I see this resistor E is this, just you can make a loop, it goes straight back to the battery. Okay. So I'm going to draw that as like this waterfall right here, this flash, right? This is like the entire height of this cliff, right? But then the current splits, right? And I got this resistor D, that's like this waterfall, this flash, right? Then it splits here to A and B. So that's like split waterfall, splash, right? You got waterfalls A and B that are side by side, so it's in parallel, so they got the same voltage drop, is what that means, right? Then they merge back together. Right? And then resistor C, that's like this waterfall, splash, right? And then you get sprouted back to the pump, back to the battery. Okay? Battery's like the pump, right? Here's that. So there you go, there's a nice waterfall model. All right. And the heights of those waterfalls represent the voltage drops, right? Which is the next column we need to figure out in the table anyway. Right? It says, what's the delta V? That's like the change of voltage, the voltage drop, measured in volts, right? Also called electric potential. Right? So change of voltage, electric potential. Right? Well, one of them I can get right away without doing any math, because I see that the height of the pump, the height of the battery, and waterfall E are the same height. Right? You guys see that? That is actually Kirchhoff's loop rule. Right? You guys remember Kirchhoff's loop rule? If you identify any loop, the voltages have to sum to 0. Right? So like this. Right? So for example, let me review this one because we're about to be applying this one. Right? You guys see this loop here? So here's a loop. What if this is like a 9-volt battery? So right there, 9 volts. Right? And I got like 1 ohm and 2 ohms. Well, if it's 1 ohm and 2 ohms, right, it's going to pump up 9 volts and then like down 3 volts, down 6 volts. So altogether, it's like up 9, down 9, up 9, down 9, up 9, down 9. Right, you guys see it? That's that one. Right. And we got a loop right here. So this is, in my case, up 24 volts, down 24 volts. So your resistor E has the same voltage drop as your battery supplies to begin with. Right? So that number has to match that number. For me, it happens to be 24 volts. Okay, you guys got that? Just copy paste that number right there. You guys see why? Okay. Okay. Now all these other ones, it's a little bit trickier. We need to dig into the circuitry. Okay, so to figure out the voltage drops for these other ones, right, let's go back to. Right. Do you guys remember a few minutes ago when I was drawing equivalent circuits? I said this circuit right here was going to be helpful in a few minutes. Well, the time has arrived. We're about to use this one right here. Okay, this is one of my middle steps. Right, so you guys are looking at your notes because you have some equivalent circuits too. Okay, so I know from this point to this point is a 24 volt drop. Right, so 24 volts up, 24 volts down. I know that. That's also true going around this entire branch. Remember, voltage thing kind of like being pressure. There's also a 24 volt drop this way collectively, but it's going to drop down a little bit, a little bit, a little bit. Okay. Now, for that series setup, I can say, go back to this page, that the voltage drop across each individual resistor is very simply proportional to that resistor on that branch, right? As long as they're all in series, right? As long as they're in series, that's true. Okay. So what's that going to look like right here? Here's what I do. I'm going to switch deep color and do some, that's kind of a tight bit there, right? Maybe I'll spread this out a little bit, right? So this fits back a little bit. Right. So the voltage drop across, and what did I label that? I labeled that D. So voltage drop across D, which is this guy right here. This is resistor D is, this down here is resistor C when I eventually get to it, right? And this is collectively A and B, right? So later. So the voltage drop across D is, well, that's a 2 ohm resistor. And if my numbers are different than yours, then watch out for that. So I got 2 ohm resistor on a branch that's 2, 3, 4, 5, 6 ohms altogether. You guys see this entire branch is like 6 ohms, which I figured out before also, right? So 2 ohms out of 6 ohms. You guys see 2 out of 6, is that like a 1 out of 3 ratio? Right, so that's my ratio, right? Ratio of what? Well, it's a ratio of how many volts drop. And from this point to this point, I know it's 24 volts drop altogether. 24 volts. So it's 2/6 of 24 volts. It's like a third of 24 volts. Is that like 8 volts? You guys think like 8 volts? Okay, so I can see what I'm saying is 8 volts drop across that resistor, okay? Because it's 2/6 of 24 volts. 2/6 of 24 volts. Right? Right. Let's say it again. Right. So I'm looking at this branch right here. I know from this point to this point, along this entire branch, there's a total of 24 volts drop. Right? Whatever your battery is, it's going to happen to match that. Right? 24 volts for me. Okay. And the voltage drops a little bit, a little bit, a little bit. Right? So in 3 stages. And each individual voltage drop is proportional to that individual resistor. So 2 ohms out of 6 ohms. So I got 2 out of 6. So that's proportion how much it drops. And I'm talking about 24 volts total. So 2/6 of 24 is 8 volts. So I know 8 volts just dropped right there. Okay. Right. Right. So I'm going to go over to resistor D and say 8 volts just dropped. Okay. Let's do that also for, here, let me skip down here to resistor C. Okay. Okay. So the voltage drop across C is, okay, now this guy's only 1 ohm. Ooh, that's half as much as the one I just calculated. So I bet it's going to be half the voltage drop also. Let's see if that's true. So you got 1 ohm out of, again, this entire branch is 6 ohms. So 1 out of 6 of a total of 24 volts. So 1/6 of 24, right? That's 4 volts. Oh yeah, look at that, right? Half the resistance, 1 ohm compared to 2 ohms, half the voltage drop for that same branch, right? It's just proportional. So I can go over to resistor C and say that's going to be a 4 volt drop. Okay. Right. And then now this 3 ohms over here, remember that really represents A and B collectively. Remember, A and B are in parallel, right? So there is only one voltage drop that represents any two resistors in parallel always have the same voltage drop, even if they're different resistances, right? That is this rule right here. Right? So for parallel resistors, it's the same voltage drop across both, right? So we're going to do a calculation that just answers both of them together, right? Now, mine happened to be the same resistance individually, 6 and 6 ohms, but even if they were different, they'd still have the same voltage drop, which might be true on your paper. So I'm going to say the voltage drop across A and B collectively is 3 ohms. Collectively, they represent on the 6 ohm branch. So 3 out of 6 of my 24 volt drop total. 3, 6 to 24. That's like 12 volts. Okay. Right. That right? Right. And if you add those 3 drops up together, guys, what's 8 plus 4 plus 12? 24, which is how much it was. That is the total, right? 24 volt battery. So I'm going to go over. I just answered 2 boxes. Right. Answered both A and B. There's going to be a 12 volt drop on each of those. Okay. Right. So you guys good there? Right. Now, if you got that whole column correct, if you followed me step by step, right, and again, you're probably getting whole numbers, I think, just like I got whole numbers. Right? I think that's probably the hardest part of this entire paper, right? Because everything else from here on out is going to kind of click in place, right? So while you guys are checking your math, let me go and point out how this corresponds to this waterfall model too. Right? These voltage drops that we just solved represent the heights of these waterfalls, right? Like the deeper the dam, the more the pressure, right? Voltage is kind of like pressure. Remember, I have a 24 volt battery. 24 volt battery. Okay. This waterfall represents resistor D. That is a 8 volt drop. I think about like 8 meters high or something, right? My resistor C down here was 4 volts drop, right? And A and B collectively together, you guys see my 2 side-by-side waterfalls? Side-by-side, of course they have to have the same height drop, same voltage drop, right? Which I said was 12 volts, so 12 volts, right? And if you add those 3 heights together, 8 and 12 and 4, yep, you get 24 volts, which is what was supplied to begin with. That's the height of the entire cliff. See how it goes together? Okay. All right, guys ready for next step? Okay, good. Okay, so like I said, from here on out, I think it's going to be pretty smooth sailing because this entire next column, current in amps, that's what I is. You guys remember I is current, electric current measured in amps. We can just figure out very simply using Ohm's law. You guys remember Ohm's law? How much current flows is voltage divided by resistance. So the more of the voltage, the more the current. The more the resistance, the less the current. Right, so kind of like Newton's second law of motion. Right? Right. Some textbooks write this as delta V over R, like a voltage change. Right? Okay, which I think actually maybe that's a more accurate way to do it. Okay. A lot of times you'll see this as a non-fraction form, V equals IR, or some version of that. Okay. So we're just going to do V over R. So zoom in here. Let's do it better. Okay. So let's do each individual resistor. So 24 volts drop across resistor E. 3 ohms is resistor E. Guess what's 24 divided by 3? Is that 8? So that's 8 amps. I got 8 amps of electric current going through resistor E. Okay? You think that like if this was a traffic flow, that'd be like 8 cars cut that way. Something like that. 8 cars per minute. Okay. 8 gallons per minute. How about that? Resistor D. What's 8 volts acting on 2 ohms? What's 8 divided by 2? That's 4 amps. Resistor C. What's 4 volts acting on 1 ohm? 4 divided by 1, well, that's 4 amps. Resistor B, I got 12 volt drop on 6 ohms. What's 12 divided by 6? That's 2 amps. Resistor A, 12 on 6 is also 2 amps. Right? Okay. And then at the point of the battery is supplying 24 volts, and it feels like it's pushing collectively against 2 ohms. What's 24 volts divided by 2 ohms? That's 12 amps, right? Okay. And before we move on to the next column, I want to make sure this story checks out. Remember, current in amps, you could use a traffic flow analogy or a water flow rate analogy, right? Right. So it's like 12 amps leave this battery and then immediately split, right? Most of that current, 8 out of the 12 amps, immediately cuts along resistor E and then just goes straight back to the battery, right? So there's 8 of my 12 amps, boom, right there, right? The other 4 amps split the other way and all had to go across resistor D. Yep, that checks out right there. There's my other 4 amps right there. 8 and 4 makes the total 12, right? And then what happened? Okay. Then the 4 amps split again and went to A and B. Oh, look at A and B. That's 2 and 2. 2 and 2 makes 4. Right? In fact, they can combine together again. And through resistor C, there's your 4 amps back together. That 2 plus that 2 makes that 4. It's another way to look at it. Right? And then it goes back. Right? So we solved this so far using which rules we used. Right? We used this proportional voltage rule, and we also used Ohm's law. Ohm's law was the other rule we used, right? But we could have solved this a different way, right? We could have been using this this current split rule, and that's kind of what we just did as a check. We were following the current story and say, oh yeah, the current does in fact split that way and does combine back together that way too. All right, guys, good so far? All right. This last column, power and watts. We're going to use Joule's law, and I gave you 3 perspectives for Joule's law. These are all power and watts. Right? I could go current times voltage, current squared times resistance, or voltage squared divided by resistance. Let me show you that it's all the same thing. Right? So for my resistor E, let's try this out. If I do current times voltage, that I times V, that's 8 times 24. What's 8 times 24? That's 192 watts. Okay. So you can imagine, hey, maybe that's like a 192 watt light bulb or something. Or you can imagine it being that way, something like that. 192 watts. Right? Or if I didn't do I times V, I could have done I squared times R. Let me show you that's the same thing anyway. Okay. And if you're getting all these numbers correct, then this should check out too. So 8 squared times 3, it's 192. Right? Or I could have done V squared over R. Let's see if that gives me the same thing. What's 24 squared divided by 3 ohms? That's 192 again. And of course, it was always going to be. So physics wins again. Okay. Okay. But going all the way down, let's just do I times V. So current times voltage. I think it's pretty straightforward, right? 4 amps times 8 volts. That's 32 watts. 4 amps times 4 volts. That's 16 watts. 2 amps times 12 volts is 24 watts. 2 amps times 12 volts is 24 watts. Okay. And your paper's working out too? Check, check, check. All good? Okay. Now we're right near there. We got 1 cell left on this table. Okay. And yesterday I mentioned that there's at least 2 perspectives for this last cell. Right? And they both better converge and tell you the same number. And if they do, then you're probably really good to go. Right? Especially if you're getting whole numbers and right? Right. So one way to get this last cell, we could just apply Joule's law at the point of the battery. So what's 12 amps times 24 volts? Let's see what it is. 12 amps times 24 volts is 288 watts, right? The other perspective, and let's check this too to make sure this works, is does electricity supply meet electricity demand, right? I got 5 resistors here that are all pulling some number of watts that better be supplied by the battery. Let's see if it does. Do these 5 values of power demanded match the power supplied? 192 watts plus 32 watts plus 16 watts plus 24 watts plus 24 watts. There's all the power demanded, right? I hope it's 288 watts. If it is, then we're good to go. Hey, it is. It's 288 watts. So yeah, electricity supply matches electricity demand. All right, you guys good? If you've got that one, then yeah, that's probably the toughest one on this whole paper. You're really good. One last detail on this number 2 is circle the brightest bulb on the circuit. Did we do this yesterday? Guys, what number would indicate the brightest bulb? How about the greatest power in watts? Greatest power in watts. So what's my greatest power in watts? Well, mine is clearly resistor E, right? It's probably also true for yours, right? I mean, if you hook resistor E in parallel with your battery to begin with, it's kind of hard to not be, right? Unless you have some crazy resistance or something, right? I'm going to go with the, yeah, resistor E is my brightest bulb, so I'm going to circle that one. Okay. All right, and that completes number 2.